So in the main video, we touched a little bit upon the epsilon-delta definition for function limits, but we didn't go explicitly into it. So in this video, I want to go explicitly into it just in case you want to know what's going on. So before we jump into that, we need to analyze the modulus a little bit more. So in the last video, we talked about modulus as being the distance of a complex number from the origin on the complex plane. And that's true, but we're going to use it more in this context. So I've written two complex numbers here, z1 and z2, and we want to find the modulus of z1 minus z2. So how are we going to do that? First, let's find what z1 minus z2 is. What complex number is it? Where does it lie? So we do this component by component. So let's take the real part of z1, it goes up to here, and the real part of z2 goes up to here. So we want to take this distance minus this distance, which is going to be negative. So it's going to be negative in the magnitude of this distance. So it's going to be right here. So, and then we want to do the same with the imaginary components. We want to go the imaginary component here minus the imaginary component here. And again, it's going to be negative in the magnitude of this distance. So going down. So now that point lies right here. This is z1 minus z2. And what do we want to do with that? We want to find the modulus, which means we want to find the distance to the origin. So now just to reinforce what we just said here, is that this distance right here is the same as this distance right here. And this distance right here is the same as this one. So what does that mean? That means that the distance we just drew, the modulus here, is the same exact thing as the distance here. Which means that whenever you have the modulus of some complex number minus another complex number, it's the same as the distance of the line segment that you draw between them. So with that in mind, let's tackle this epsilon-delta definition limit as I've written it here. So I'll read it again. It says that the limit of f of z as z approaches z0 is L if, given an epsilon greater than 0, there is always a delta greater than 0 such that the modulus of f of z minus L is less than epsilon when the modulus of z minus z0 is less than delta. So this still seems kind of complicated, but we'll break it down and use what we just learned about modulus right here. So now pretend that our z0 is right here, and let's say our limit that we think is the limit of the function at z0 is right here. So how do we check this? Remember what I said in the previous video about how this is kind of we talked about how this is an epsilon-delta game. And how do we kind of look at this? So first we pick an epsilon, and that epsilon is going to be the radius around the open disk centered at L. So here's the epsilon, and here's the open disk. And why is it the radius? Well, it's because what this says. This says the modulus of f of z minus L, which we just learned was the distance from some f of z to L. So we're saying that that distance always has to be less than epsilon. And if it was less than or equal to epsilon, then it would include all these points around here, around the circle, where the distance is exactly epsilon, and everything inside. But since this is an open disk, we're only considering this inside portion. So we're only considering the points where the distance from that point to L is less than epsilon, is less than that outer radius. So this is why this form, wherever you see it in future videos or this video, always denotes an open disk, a circle, but only the inside, because it's only what's less than. So now let's dissect what this is saying. It's saying that the f of z minus L, that modulus, will always be less than epsilon whenever some other radius, delta, so let's use gray here, around centered at z0. So again, it's an open disk. Anything inside here. So whenever we pick something inside here, inside this disk, it'll map to something inside this disk. And what does that mean? That means that let's say we pick something far away but still in the disk, that'll probably map to something farther away in here, still in the purple disk. Now if we pick something really close to z0, that'll most likely map to something much closer to L. So like that. And now this is saying that no matter what size epsilon you pick it as small as you want, and you pick an open disk centered at epsilon, centered at L with that radius epsilon. So to draw that, we'll make a bigger portion. So here's L drawn bigger, kind of zoomed in, and we pick a really, really, really small epsilon. And again, remember what we're talking about. We're considering all the points that are inside this disk. We want to find the delta so that, and let me draw this up here. So here's z0 zoomed in. Let's pretend there's this delta, which is the radius of this disk, such that whenever we pick something in this orange disk, it's going to map to something inside this blue disk. So we're saying that if this limit truly exists, then it must be true that we can pick as small epsilon as possible, any epsilon we want, as small as possible, and we will always be able to find a delta, so that when we draw that circle around there and pick any point inside, all those points map to only the points inside the epsilon disk centered at L. So that hopefully kind of would help to understand how this works. Whereas with single variable calculus, we see that epsilon is more like a distance on the y-axis. This is more like a radius. In fact, they're both radii. And you're just showing that whenever you have an epsilon here, you can always find a delta, so that these points in here always map to points inside the blue disk. So hopefully that kind of helps. But the main thing to take away from this video is that whenever you have a z1 minus z2 and you find the modulus, that is always representing just the distance from here to here. And that we kind of applied in this definition.